This first example says, determine the final momentum of a bike rider who was initially traveling at 4 meters per second, then subjected to the free body diagram below for 10 seconds. So the first thing that we want to do is we want to say, okay, if I'm trying to solve for the final momentum is going to be the mass at the final and the velocity at the final. So those are the two things that I need in order to make this work. So if I were to look at this particular situation, I would realize that no matter what forces I exert on a particular object, the mass is not going to change. So the mass is going to stay the same regardless. So really what I need to do in order to get this to work is I need to solve for the final velocity. So the first thing that I need to do is I'm going to go ahead and work through these forces and kind of see what I've got going on. The first thing is if you were to look at the free body diagram, you would say, okay, the normal force and the gravitational force are equal and they cancel each other out. Okay. You also have the fact that you have a frictional force and an applied force, and those don't quite cancel each other out. And what they leave you with is they leave you with a combined sum of the forces of 10 newtons, and it would be to the right. So you have a combined forces of that. Using the sum of the forces, I can calculate the acceleration of this particular object. And what I can do is I can say, okay, the sum of the forces is equal to the mass times the acceleration. Well, in order to do this, I need to know the mass. Well, remember, if you have the weight is equal to mass times gravity. There's a lot of review going on this particular example. So what I can do is I can say, okay, well, if I have a weight of 490 and I'm on Earth where gravity is 9.8, you can go ahead and say, okay, well, then the mass is 50, and the mass is 50 kilograms. So now I can go ahead and say, all right, well, if I have a sum of the forces of 10 and I have a mass of 50, that allows me to solve for A. And A in this case would be 0.2 meters per second squared. Now with an acceleration of 0.2 meters per second squared, you can now say, okay, well, I've got the initial velocity, and that was 4 from the problem. I've got the acceleration, which I calculated to be 0.2 meters per second squared, and I have the time to be 10 seconds. Using those three things, I can use my kinematics motion equations, and I can solve for the final velocity. Now, if I were to do if dat, I have the initial, I have I'm looking for the final, I have the time, and I have the acceleration. So the only thing that I don't have and don't care for would be the displacement. Well, that means the equation that I would choose would be final velocity equals initial velocity plus acceleration times time. Or in our particular case, I would say the initial velocity is 4 plus the acceleration is 0.2 times 10. It looks like I'm running out of room here. So you would multiply 0.2 times 10 and you get 2. And then add it to 4, you would get a final velocity of 6 meters per second. But remember, this is not what you're looking for. You're trying to solve for the final momentum, which means you need to take the mass, which we conveniently have right there, and we have the velocity, which is right there, and we need to plug them in, and we need to be able to solve for momentum equals mass times velocity. So we plug our values in, and when we do that, we get 50 times 6, which is 300 kilogram meter per second. Okay, that example had a lot going on. We had to read the free body diagram. We had to solve for the mass using the gravitational formula. We had to then plug our variables into the kinematics equation. Once we plugged them into the kinematics equation and solved for final velocity, then we had to use the momentum equation. So you can see there's a lot going on in this particular example. Now, most of the momentum questions you see aren't going to be that difficult. If you look right here, it says a car is released from rest and allowed to roll down the ramp until the styrofoam block is shown. It says sketch the relationship between the distance the car is allowed to roll and the momentum of the car as it reaches the bottom. This is a little bit more complicated than it looks. So first of all, we need to label our axes. So this is going to be distance, and we'll call it meters, and this is going to be momentum, and we'll call it kilogram meter per second. So, if we were to look at this, we have the equation that momentum equals mass times velocity. Okay, and that's really good. In this case, it's going to be the final velocity because you're looking at the momentum as it impacts. Now, the problem is that distance is not anywhere in this equation. So what I need to do is I need to be able to figure out a way to get distance in that particular equation, but I need to make sure that my variables are all consistent. So, because I'm leaving the track at a constant elevation, I can say that the acceleration is a constant. I'm going to be releasing the car from rest, so that right there is going to allow me to say the initial velocity is 0, which is also constant. Using these things, I can also incorporate the distance formula, and I can say, okay, final velocity is equal to squared is equal to initial velocity squared plus 2AD. Okay, you may be thinking, okay, well, how is this related to whatever I'm trying to do here? What I need to be able to do is I need to be able to say, okay, I need to substitute something with distance in to this particular equation. When I do that, I'm going to end up getting something that looks like this. I'm going to substitute in P is equal to M, same thing here, and now I'm going to substitute in what VF actually equals, which is going to be the square root of VI squared plus 2AD. Now, when you are graphing two variables, the only thing that matters are those two particular variables. So, I can say mass is not on this graph, so it's irrelevant. It doesn't go away, it's just kind of a constant at this point. It becomes a regular number. Same thing with initial velocity, which I know is 0. Okay, 2 is a number, and then acceleration is a constant number as well. So those kind of go away in terms of the graph. Now, if I was calculating this out, I couldn't do this. But it's one of those things. This is a graph, and it's very different. So now what I end up with is P is equal to, or we wouldn't really say equal at this point. We say P is proportional to the square root of the distance. Okay? If you have P is proportional to the square root of the distance, you can now substitute in. You can say, well, P is on the y-axis, so I can say y is proportional, in this case, to the square root of x. So what I can do now is I can say, okay, my graph is going to say y equals the square root of x. So if I were sketching the graph, it would look something like that. Now I know it's not going to be perfect in terms of it's going to be exactly proportional to that because we have those constant numbers that we threw out. But those constant numbers will either raise the graph or lower the graph, but it will maintain its same shape. So if you look, as you increase the distance along the ramp, you're not having the same proportional increase in the momentum. And the reason why is by increasing this distance right here, you're not really affecting the velocity as much as you normally would. And if you're not increasing the velocity in a direct relationship, then you're not increasing the momentum in a direct relationship. This is a tough question because it requires you to know a lot of things and pick the right kinematics equation. If I would have picked a different one, it might have showed a different relationship, but I can't do that because a lot of people will say, oh, well, time is constant. And it's not, because if you start the car here and you start the car here, it's going to have different times to get there. So I couldn't use one of the equations with time in it. Like I said, this is a tough question, one you really got to be able to think through. This one is a little bit easier. It says determine the momentum of a 5 kilogram bowling ball thrown at 14 meters per second. So we want to go through the guess method as we normally do. We say mass is equal to 5 kilograms. We say velocity is equal to 14 meters per second. The equation or what I'm trying to solve for is I'm trying to solve for the momentum. So I've got my given and my unknown. Now I can substitute my equation in there, P equals mv. Once I've done that, I can now take these and I can plug them in, and I can say 5 times 14, and that equals 70 kilogram meters per second. So that right there represents the momentum of this particular ball. Now really I should have a direction here, and based on the picture I want to say left because I'm going to assume that the velocity was to the left based on this particular picture. So now you should have a pretty good grasp of what momentum is, and you should be able to calculate momentum, velocity, mass, given those appropriate variables. And you should also be able to do the things with a graph and relate all our kinematics motion to these things as well.